Good evening. Oh, that's better. Okay. Right, well, sorry about the slight delay there. Everyone's all out with technology. It is all frighteningly complicated, but welcome. Just finding another bit of technology here. Well, welcome and welcome to the beginning of the 2023-24 lecture season here in Queens. We're very grateful to Queens as always to learn in this room and all the help they give us. And we've got Alan Fitzsimmons who looks after us here to give a round of applause for coming to you. Now, I've got a few things I just want to go through before we get started. Just as soon as the technology starts working. There we go. Right, so first of all, you've probably not had this done before, but we do now have to mention a little bit about health and safety, because that's the age in which we live in. Just simply that if we do have a fire alarm and we have to evacuate the building, there are 3 fire exits in this room, and there are 2 at the back, and the one to the bottom right of the lecture again here. I'm absolutely not sure where you come out if you go like that one, so...
You come out where the fire is, generally.
But the 2 at the back, you know where they go, because those are the usual exits we use. So that's that. Now we've got some program cards and membership forms down the front here. If you do want to pay your subs, we've got Pat and Mary here this evening. There's Pat and there's Mary just there, and up thank you very much. And it is still the bargain price of £20 each or £25 for a family, which is fantastic value. It's been that for about 12 years now, which is quite extraordinary. I'm going to talk a little bit about the lecture programme for the first part of it, certainly. And is somebody here able just to mention a few words about the observing programme? Because I should mention that we've changed all of that since COVID and so on, not least because we can't use Delon Country Park anymore, because there's health and safety things. I suppose that man comes around about 9 o'clock in the evening and locks the gate now. So we now have a use of a place in Clandy Boys, which is just sort of between Bangor and Newton Ards, kind of in the area. It's not bad, it's for people I'm told. And Terry's teaser, and then I'll talk a bit about the sky. And then, of course, the main act that we all come to see me. You come to see Professor Tom Ray, our speaker from Trinity College Dublin, of course. So, was there anyone, Andy, did you want to just say a couple of words about the observing?
Yeah. The observing, as Paul says, is in JWST Estate, and there's been quite a few people actually coming down from Belfast. Just head into Belfast, into Bangor, down the Bangor Road, and the JWST Estate is on the right-hand side. You have to be careful, because it's dual carriageway, it's very busy, and you'll be crossing it into Clandyboy. You go through the gates, the main gates of Clandyboy, there's a little house on the corner, and you go 150 yards, and there's a turning on your left-hand side. And I have to say it's been really excellent. It's not a perfect site, it's not as good as Dalmont, but it's more social. There's a little house you can go into and keep warm, and also we've got the 16-inch, the club 16-inch telescope there, and we've also got an 8-inch at the moment, it could be an 11-inch, and we can project the images from the telescope into the classroom. So that's the setup we have at present, and you're all very welcome. We're going to try and do the observing, as Paul probably say, the first Friday following the meetings. If it's cloudy, we'll try the Saturday. If it's cloudy, we'll go to the next week and we'll try Friday or Saturday. And if it's still cloudy, we'll leave it to the next week. So that's it. Thank you.
That's brilliant. Thanks very much, Andy. I'm sorry to drop that on you, but I would be in a situation where I didn't know what I was talking about. So try and avoid that. Right, let's have we look at the lecture programme. Terry's put together an excellent programme here now. Terry will tell me that there's an amendment to this that I haven't put in there yet. But tonight, obviously, we've got Professor Tom Ray talking about JWST telescope, and that was brilliant. Next fortnight, October the 4th, I shan't be here myself, sadly, but Rob Hill is coming down to talk to us about how the space economy works in Northern Ireland. There's a lot of companies now here involved very much in work and space, and Robert sort of pulls it all together, so that'll be a good talk. Richard Goodrich, Fear and Loathing in the Heavens, and that's all about the 1910 return of Halley's Comet, a long time ago. I did see Halley's Comet as a very faint smudge in binoculars in 1986. Apparition was much more impressive. So that was good. Some guy called Paul Evans is talking about rockets on 1st of November, and for a change, I'm not be talking about Apollo and rockets. I'm going to have a stab at putting together a talk of, as much as I know, and it is a bit of a moving target, about the Artemis program, which we've already had Artemis 1, which is an unmanned moon mission, and there are further Artemis rockets going up over the next few years. And I'll try and put together the best I can an outline of what's going on there. So that's the 1st of November. 15th of November, Dr. Elizabeth Butler from Queen's here, who was talking about solar mysteries. And I think Dr. Matt Nichol from here from Queen's is not going to be on the 29th of November, he's going to be on the 10th of January, and that is your first date back from the Christmas New Year break, so just make a mental note of that. And Terry, you've got some, haven't you?
Chris Watson has lined up somebody for November 29th, but that is still to be confirmed, and if not, I have somebody else's planned in. So
right, so watch this space, we'll fill that behind as soon as we can, and likewise it will be a couple of Allen students will be putting together something for us on 13th of December, so that's the lecture programme as far as we've gone with it. Mark that date at the beginning of next year, 10th of January. I think somewhere said the 3rd of January, I thought that's far too soon. There we go. So Terry, do you want to give us a good tease?
Right. This is in 2 parts, and you need to have the answer for both parts, otherwise you don't get anything. First of all, can the James Webb Space Telescope image the Hubble Space Telescope, and can the Hubble Space Telescope image the James Webb Space Telescope? So unless you're prepared to answer both of those, don't say a word.
No and yes.
Speak up.
No and yes.
Right, and why?
Well, it seems to can't face towards the Earth at all, because the way it's set up, it's always facing away from Earth. And the Hubble can more or less point towards Lagrange point behind the moon and pick up.
Very good, that is correct. The James Webb Space Telescope cannot point in towards the inner solar system at all, because it has to look out into the sort of the very cold outer universe. It literally cannot point in anywhere in our direction. The Hubble Space Telescope can just about image the James Webb, which is a million miles further out. It can't resolve it, but it can just show it as sort of an image on a pixel, as if it was a very, very faint star. So yes, the answers are no and yes, well done. And I don't have any Milky Ways with me, so I have a choice of a Mars bar or a Mars bar. Right? That's it.
Thank you very much, Terry. I think I'd want to know there myself, because they're a million miles apart.
Yeah.
So it's got to be a very difficult thing. As you say, probably would show up as a pixel. But yeah, so that's great. It's a great question. I like that. Okay, well, I'm going to just talk a little bit about the sky. I would say the night sky, but this isn't obviously, because this is the daytime sky. And the sun is getting very, very busy, and solar cycle 25 is really sort of proving to be somewhat ahead of expectations. We thought that solar cycle 25 would be somewhere much the same as 24, but it seems to be already ahead of where 24 was at a similar time there. And the sun, you see, is quite spotty. There's plenty going on there, and there's this group here, I'm quite interested in this coming around. We're sort of hoping that something will explode when it's facing us, not hopefully when it's facing us directly. Because we wouldn't want to be having another Carrington-style event at this point in time. Carrington event took place in 1859. There was a huge sunspot explosion directly at the Earth. And we didn't have computers or satellites or power grids or anything like that then, but we did have telegraph networks, and the operators in the United States did actually get electric shocks from the induced currents from this explosion. They got auroras in the Caribbean, which is pretty much unheard of, and stuff like that. So we like exploding sunspots because we see the aurora and stuff, but not so much so that we would lose our satellites and all that sort of stuff. So keep fingers crossed. I have had actually a very good couple of weeks myself. I got a visible aurora last week, on Tuesday, and also on Monday night this week. I'll show you some pictures from that in a moment. It's a good time of year to be doing this because the way the sun and earth magnetic fields line up, there's this thing called the Russell-McLaren effect, where around the equinoxes you've got both vertical in relation to each other. And it just makes it that much easier for the Earth's magnetic field to suck in the solar wind that then interacts with molecules in the upper atmosphere and flows nice colours. So that's how this works. You can see that this is the best time of year. September, particularly in March also, the equinoxes are very, very well placed for good auroras. So I went out the other evening, and this was the view from my local beach. I have to say, I did this deliberately actually. I moved sort of 400 yards from the beach in Valley Alley, and I can just scroll down there, and my phone is beeping away. I can just sit on a little table with my portable camera and tripod and just take pictures like this one. And this was Tuesday or last week as well, and it's kind of quite nice. However, not as good as it was the other night, and that's what I was getting in Valley Alley. That's three pictures stitched together actually. But if you do some thinking, people always ask me, "Oh, did you see that?" I thought, well, not quite actually, because my little camera, f1.4 lens, which connects lots of light, ISO 1600, which is quite sensitive, and 10 seconds exposure. Now, the eye does quite well at two of those. Actually, the eye is about f1.7, and its sensitivity can sort of equate to a sensor that's about ISO 1600. You can see reasonably well in the dark, but although the eye has no shutter as such, the way it reads light is about equivalent to a shutter speed of a 30th of a second, and that's not 10 seconds like what I've done here. So what I've done, just to manage your expectations on this, if you go up expecting to see that, you won't. I mean, maybe you would in Iceland or Norway or something, but Valley Valley you won't see that except on the long exposure of the camera. You will see something like that. It's the same thing, and it's actually better a bit with the eye because all of this sort of, these rays and stuff are moving, and the eye sees that movement because you've got an effect on these slow shutter speed. But you don't see any red, hardly. If you do, it's like a white fog, it doesn't light up as colour. The eye is particularly sensitive to green, so you will sometimes see some greenness in that, but really you don't, I'm afraid, see that. Only the camera does that. But that's sort of, I'm telling you this because you'll go out and say, well, I didn't see that. I was there, you see. So that's all about the sun and the auroras. If you want to find out more about it, there's a particular page on our website which looks like that, and there's some addresses there. If you want to photograph that, I don't want to photograph those web addresses. That's where I sort of gather my information from as to when this is all going to happen. The moon. Now, the moon is out at the minute, and we are sort of here. It's 20th day, so we are, at the moment, there's a sort of 5-day-old crescent moon in the sky. This is a very poor time of year to be observing crescent moons, because think of the angle of the ecliptic. In September, that moon just sort of moves along the horizon very much. It's not very high up at all. If you were to look, say, February, that's a much better time than doing that. So, but you will get first quarter in sort of on Friday, and the full moon is 29th next week, and then it starts to wane and it sort of rises after midnight, and then so comes down to the third quarter, and so we go into October. October's really here, but it's a bit like that. The new moon, I think I decided, is, well, this is 14th September, so it'll be about 12 of October then. So that's the moon phases. Yeah, if you're looking for the aurora, it's just better that the moon's not involved as well. It'll sort of wash out the sky a bit. Likewise, if you're looking for deep sky objects, the moon is a bit of a nuisance. I just find that I look at the moon if it's in the sky, really. I find it an incredibly fascinating object. Now, what have we got? Saturn, yeah, Saturn is available in the sky, so it's a little bit dark. Saturn is about 15 degrees above the horizon, 10 o'clock in the evening or so, and it still looks pretty good. It's sort of setting a little bit into the twilight now, but it was in opposition at the end of August, but it's moving a bit past its best now. But you can, that's a telescopic view, you can see Saturn. The rings are closing up a lot now. The rings will be edged on by about 2025. And you can see you can tell the past opposition here because that shadow there is beginning to appear. Around the time of opposition, that shadow completely disappears. That was the end of August, so it's beginning to come back now. You can see the rings, so fairly well. If you look, binoculars will sometimes show Titan. If you sort of do overexpose webcam views and stuff like that, you can show up some of the movements of Saturn as well, quite easily. Jupiter is very well placed, not far above Aldebaran and the Seven Sisters. Along there you'll see Jupiter, and Jupiter more closely again, you can see the equatorial band at the right time, which that is. You can sometimes see the Great Red Spot, which is a huge storm that's been going on for about 300 years. And you can see the 4 Galilean moons quite easily just with binoculars and small telescopes. By the way, I was just going to mention in relation to Saturn one helpful thing. Somebody did ask me, can I see Saturn's rings through binoculars? To which the answer is sort of mostly no, really. You actually need to see the rings as obviously rings. You sort of start at about 30 to 40 times magnification and work up from there. But 10 by 50 binoculars, 15 by 70 binoculars, if you have a keen eye and you examine Saturn through those, you may be able to tell that it is not round. That's really, you can sort of see it as a slight oval. You can sort of go, that's not a disc. You know, but really, 30 to 40 times magnification on the telescope will show you the rings of Saturn. Likewise, those bands of Jupiter, small telescope, binoculars will show you the 4 Galilean moons. And the Galilean moons are actually an interesting thing that Galileo in 1609 first saw those through the little telescope. And he was able to discern that the moons were in orbit around Jupiter. And the trouble with that was that it contradicted every theory of everything at the time, which was that everything went around the Earth, which we now know is absolutely not the case. So he got into trouble and stuff like that. But we also learned a lot of science from it. We also actually examining the orbit of Jupiter around the Sun and the moons of Jupiter around Jupiter enabled scientists at the time to have a fairly good stab at the speed of light, because it seemed to be a clock that was going in and out of the correct time. And they did have a good stab at it that was not far from being wrong, actually. And that was 80 years before any determination of the speed of sound, which ought to be much easier to measure. That's one of the great feats of astronomy. Now, if you're an early riser, and I sometimes am, although it's completely involuntary because I have to go and set up a TV studio in the morning, Mercury is visible over the next few days. Kind of about 6 o'clock in the morning. We'll see Venus. Venus is extremely bright at the minute. In fact, Venus yesterday was the very brightest it ever gets. The combination of distance from the Earth and the percent illuminated by the Sun conspired so that yesterday Venus was like about magnitude -4.5, which is as good as it gets. Mercury is visible lower down, and that's Mercury there. Just looking east, you've got a good clear, preferably across water or something, views to the east. You might get a chance to see Mercury, and although Mercury is quite often brighter than Sirius, the brightest star, because it's always quite close to the sun, only about 1% of the world's population have ever seen it, which I find astonishing, but there we go. One more thing. I think we've missed this. But there was a comet, this one here, 2023 P1 Nishimura, and really that is now scraping along the horizon. And I think we're just about had that. But did anyone get to see it by any chance? Probably had a little bit of a window, but we've not had the weather really for a while, actually, so that is the thing with comets. But, and you also see on this, what I was saying about this not being a great time to be looking at the moon is really, really low there, even present. So that's that. So, okay, so that's what's in the night sky at the minute. I just want you to stay safe and keep looking up. Now, I'm going to just give you a brief intro to our main guest this evening. Excuse me while I... Right, our guest is Professor Tom Ray. I've reached that age in life now where I need to find my glasses. It's getting used to all this, I'm afraid, is just a bit oh, here we go, that's better. Right, so Professor Tom Ray is come to see us from Trinity College, Dublin. He's made research interested in star and planet formation, in particular the supersonic jets that stars like our sun produce when they're less than 1 million years old, as well as the disk that surrounds such stars. And Tom is the co-principal investigator of the mid-infrared instrument from JWST Space Telescope. This is just out of date now, so you still are, aren't you? Yes, it just says that which is due for launch in 2021, isn't it? We never keep launch, and it's in service whenever. And Tom is the best person to talk to us about that, so welcome Professor Tom Ray.
Now, you can hear me okay, yes? Good. Right, perfect. Now, the first thing before I forget, right, this is a talk about the Webb telescope, and for those of you who are interested later on, you can come down and get some Webb stickers, Webb bookmarks, and they're there for the taking. So, the first thing I have to say is thank you very much to the IAA for giving me this opportunity to tell you a bit about the Webb telescope, but also the fantastic results that we're getting in the first year. I've been involved with this project now for 20 years, more or less since its inception, and as a result of that, we have guaranteed time on the telescope, which the group in Dublin and the international groups that we're involved with have really exploited and got some really excellent results. Okay, so let me just remind you about the telescope itself, a few things about the instruments. We'll start with the telescope. It is a collaborative project between NASA, obviously NASA are the lead, but also the European Space Agency, hence the involvement of the UK and Ireland in the Webb telescope, and also the Canadian Space Agency as well. So we've all come together to try and build this, as I said, over the last roughly 20 years. Europe was guaranteed, as a result of its involvement, roughly 15% of the time. What's interesting, I wouldn't shout it too much, there's also a lot of US people in the audience, we get about 30% of the time in the telescope. It seems likewise for subsequent cycles as well. So Europe is doing very well at this time. It's the largest space telescope mission ever launched. It was extremely complex affair, as you might imagine. But to emphasize the fact that There was a total of 14 countries worked to build JWST. You can see the south of Ireland hanging on there at the edge. Germany is also sort of floating away there. The UK seems a bit more pinned onto the middle, but there we go. So, this is back 10 years ago, roughly 10 years, we had the whole JWST team in Dublin, in the Royal Hospital Kilmainham, for the NASA ESA CSA conference, where we're discussing different aspects of design. That's a full-scale model in the background, and as I think Terry and a few others know, I got into an awful lot of trouble with the director of the Royal Hospital Kilmainham, because that's also the Irish Museum of Modern Art. And apparently a lot of people were going around the grounds thinking this was some piece of modern art. And he was a little bit upset about it. But in the end, we persuaded him to leave it there for 6 weeks. So, the involvement of Europe, well, a couple of the instruments include the one I'm involved with, the mid-infrared instrument, and also the near-infrared spectrograph. I'll show you pictures of those in a few moments. But the other thing Europe did was provided the rocket. And this was from an Ariane 5 rocket. The launch was from French Guiana. It was December 25th of 2021. We were due to go out for the launch, but then there was an outbreak of COVID in French Guiana, and so in the end we couldn't actually travel. But certainly Christmas Day 21 was a very tense period in the Ray household, if you might imagine. But we broke out the champagne once it had gone on. This is an actual picture. I was almost about to say one of the last pictures of JWST, but you can, as Terry has mentioned, you can image it from the Hubble Space Telescope, but you can just image it from the ground as well. It's bright enough, even at the distance that it's at, that we can actually see where it is at any one time. So why I'm showing you this picture is that the camera system for showing JWST was developed by an Irish company, Railtrug, which means of course star, and they provided the system to the European Space Agency for doing all this telemetry work and video work. So, I still have to, no, I won't go through the launch. We've all seen JWST being launched. So here are some of the basic numbers for JWST. The first, the important point is that the mirror, let's see if we get this working. Yep. The mirror is about 6.5 meters in diameter, but you'll see it's actually a gold mirror. And it's gold because gold, if you like, is a bit like silver, in the sense that its reflectivity is perfect in the infrared. Right? So silver, of course, is really, really good for optical light, but gold is perfect for infrared light. And so it's an infrared optimized telescope. Externally, it's cooled to about minus 230 degrees Celsius, or for those of you who know about Kelvin, it's about 40 degrees Kelvin. So 40 degrees above absolute zero. But the instrument we work with, the mid-infrared instrument, is actually cooled to about 7 degrees above absolute zero. Some of you may have heard of the 3 Kelvin, the 3 degree background, 3 Kelvin. So it's just a few degrees above the background from the microwaves. Okay, so let me give you just a quick tour of the instruments and what they do. We have, and this is an instrument that's been used an awful lot. Many of the images that you're seeing from JWST come from the near-infrared camera, which was largely produced in Arizona with the help of Jet Propulsion Lab, JPL in California. It operates from 0.6 to 5 microns. Now, just to give you an idea about that, typical sort of yellowish light is around 0.6 or so microns. So optical light is around 0.6. So it just starts in the optical, but it then goes up to something like 10 times optical light, right? Which is why, incidentally, as you'll see later on, the telescope is perfect for imaging stuff that's a redshift of 10. Right? Perfect for that. Because the optical waves from the galaxies, which are 0.5, are shifted to 5 microns. And it's got narrow and broadband filters as well. It's got a long and a short wavelength modules. One basically goes from 0.6 to about 2.5, and the other one goes from 2.5 out to 5. So that's the basic near-infrared camera. The spectrograph, the near has a load of little shutters. You can define where you want to open these shutters. I hate this picture because it shows look like a pencil read stuff in this rather delicate instrument. I'm sure it's not that. But anyway, there are thousands of shutters, and these can open at user-defined positions, which means if you're looking at a field with a load of galaxies in it, for example, you can open it up at the different galaxies. So you don't waste any of the light, you can concentrate it on certain areas. And so we use these micro shutters, and similar range in terms of wavelength to the near-infrared camera, but it's actually doing spectroscopy. And spectroscopy, some of you know about the resolution of the telescope. The higher the resolution, the more fine detail you can see. But in the same way with spectrograph, the higher the detail you can see at individual wavelengths, then the higher what we call spectral resolution is. So you have, if you like, visible spatial resolution, and then you have spectral resolution. And it's a few thousand. So it means, what it means is we can detect lots of different lines in the spectrum with very high precision. And that instrument, by the way, was also NearSpec. That was built in Europe, in addition. And what you can actually do with NearSpec, by the way, is take a little bit of a galaxy or a little bit of a star formation region or a region around a star, and you can actually break up the light into a cube. Right? Essentially what you're doing is looking at different wavelengths in that area. So it's a bit like as if you had thousands of filters. The way in front of the sun you see a H-alpha filter and just have the H-alpha light. But in the same way you can get a whole range of wavelengths in one go. And that's of course very interesting if you're trying to detect certain elements or trying to detect motion as well in the gas that's there. So that's the NearSpec. And then we have another instrument called the near-infrared imager and the spectrograph, NIRIS. And the difference is that it allows you to really big field, not very high spectral resolution, which can do big area and get low resolution spectrum. Ideal when you want to, for example, look at an exoplanet around another star, because there you don't have very much light, so you can't really afford to stretch it out over lots and lots of sub-wavelengths. So this demonstrates the power. I'll go into the different results now in a few moments, but it just demonstrates the power of NIRIS. This is actually a star here, which one of the WST, I'm trying to remember the number, 96B. I'm very bad with these telephone numbers. But this exoplanet was studied here with NIRS, and what you can detect in this exoplanet is actually lots of water. Now this is a kind of hot Jupiter. It's very, very close to its star. That's why it's hot. It's kind of Jupiter size. But look at all this water in the atmosphere of WST 96B. I mean, when I saw the spectrum first, I thought this is like a sort of Turkish bath exoplanet, because it's just full of steam, right? And there are some other more molecules. Okay, and then there's the instrument that I've been involved with for, as I say, around 20 years now. So my institute, the Dublin Institute for Advanced Studies, was involved in building part of that and testing part of it. It operates at much longer wavelengths. So I said the near-infrared camera operates from the optical to, say, 10 times the wavelength of optical light, 5 microns. This goes from 5 to 30 microns. So it's very much into the infrared. Now, at this point, it's a good juncture to say, well, why put this in space? Okay? But apart from, I think, many of you know the benefit of something like the Hubble Space Telescope, being in space, it actually benefits from the fact that you don't get the blurring that our atmosphere causes. Right? And that's it. I think most people know that. Well, there's another reason when you come to these wavelengths, because those sort of wavelengths from 5 to 30 microns are basically the wavelength that the sky is burning at. That's the only way to describe it. So the sky, even in Ballygoy or wherever you happen to be, in the middle of the night, and you look up, okay, optically you see, oh, that's dark, and I can see plenty of stars. But if you look in the infrared, if your eyes were capable of looking in the infrared, or you had special infrared detecting equipment, what you would see is the whole sky would be blazing. And the reason is the same reason that some of you may have seen infrared pictures of people or cats or whatever, and you see them glowing in the dark. You don't need illumination because you're actually producing your own infrared radiation. And the sky, the same way, is producing this infrared radiation. So, despite a faint galaxy or whatever, it is literally the needle in the haystack to try and find that, because the whole sky is blazing at the same time. However, if you go away from the Earth over, 1.5 million kilometers away, it's extremely cold, it's away from the Earth, and you can then detect this infrared radiation. So it does spectroscopy as well with a resolution of 2000 for those of you who are familiar with this. But the other thing you can do is coronography, which means in other words you can block the light of the star. Now why would you want to do that? Because you might want to see the exoplanet around the star, or you might want to see the dusty disk that surrounds the star. And in that case you want to block the light so that you can get the full range of contrast. This is actually what the Dublin Institute for Advanced Studies was responsible for. The wheel came from Heidelberg in Germany. We were responsible for these filters here. Which incidentally, when you look at the filters, you can see they're little mini versions of the JWST mirror. Right? So they're matching the aperture of the mirror because we don't want that to stray out. Okay. Now, so for those of you, and Alan was telling me he was in Baltimore a couple of weeks ago, what does mission control look like? It's this. Right? And my daughter saw this and said, that doesn't look like mission control. They expect a lot of lights and all the rest, but this is actually the mirroring control panel in Baltimore, and it's in Baltimore where the Space Telescope Institute that JWST is controlled from. Right, so let me just tell you, first of all, before I go through some of the objects and some of the interesting results, when we look at something like the set of galaxies, for example, this is called Stefan's quintet. It's 5 galaxies, actually 4 of them are in the way, and those galaxies then are gravitationally interacting with one another, but this is an image from the near infrared camera. So this is at sort of wavelengths of 1.5, 3 times, 4 times the wavelength of light. So they kind of look like optical pictures of the galaxies to some degree, but obviously we can see an awful lot of detail compared to ground-based telescopes. But if just for comparison, you have a look at it with MIRI. This is in the mid-infrared, so we're talking about wavelengths kind of 10 times longer again. Right? You see something very different. This is the same set of galaxies, right? And what you're seeing there is actually dust, heated dust, which is radiating away. Right? Obviously, the source of that energy is the stars. But what you have here is you see where dust is present, where new stars are forming. So you get a very, very different picture, and it's really useful when you're trying to understand what's happening between the interaction. Perfect, thank you very much. The interaction between these galaxies, and you can see the star formation that is actually being triggered between the galaxies as they gravitationally interact. And again, with MIRI, I'm just demonstrating what MIRI can do before I show you some of the results, is you can take something like Stefan's quintet and slice the image up and look at the different wavelengths. So what you can do is actually look at the different wavelengths, and therefore look, and I think many of you would know, different elements have, if you like, a fingerprint, which you can see in the spectrum. So here there's argon, ions of argon, so charged argon, neon, and so forth. And this is molecular hydrogen. So we can actually image what's happening in these galaxies in different atoms and molecules as well. And this is very, very useful when you're trying to understand. It is automatic.
Yeah, I think apologies there, but I think this is a safety thing. It doesn't want us tripping over in the dark.
This is such an intelligent system, isn't it?
Just one more.
Oh. I can only push one of these buttons to go really dark, so if you want to okay. All right. Okay, well, 1 or 2 pictures now I want to darken. So, some of you may have seen this first slide image. The first slide image, this is just a star. You can see lots of spikes out of the star because of the complex mirror that JWST has. But what's interesting is all these background objects. They're all over the place when we look at JWST image, and those are galaxies. They're actually, many of them are very highly redshift galaxies, really, really distant in time as well. For some reason, Alan is not coming out. Say nothing. I'll just continue. Right, and I think many of you would have also seen this first image, which was a deep field. Hubble did a deep field. The director of the Space Telescope Institute in Baltimore decided he had discretionary time and he would spend literally a few days looking at one part of the sky, smaller than the diameter of the moon on the sky, and just stare and build up the image area. Right. And the whole idea was to go as deep as possible with the Hubble Space Telescope. But this image from JWST, that was done in just a couple of hours. So our in the pipeline at the moment, even deeper images than this, and they're producing some very, very nice results, which I'll talk about very shortly. But again, those you can look at those galaxies, so you can image them with, for example, the near-infrared camera. You can image them with MIRI, but then you can do, for example, spectroscopy with NIRSpec and actually look at individual galaxies. Remember I said with NIRSpec you have these little shutters, so you can say, I want to look at that galaxy, then that galaxy, and that galaxy, because it looks like it might be very, very high redshift, in other words, enormous distances away and very far back in time. And what you see here is the actual individual spectra of these galaxies here, the ones that are marked here with the little box. And you can see that there's these are the same lines, but some of them are very, very highly redshifted. You're talking about going back in time something like 13 or so billion years, up to basically a few 100 million years after the Big Bang itself. So how can we see these galaxies so easily with James Webb? I said right in the beginning that it was optimized for the infrared. So think about it. A galaxy like our own Milky Way or the Andromeda galaxy or whatever, most of the light is in the ultraviolet and the optical. Now, if you go to a galaxy very far away, that means it's very highly redshifted. So you'll have seen figures like this galaxy is Z equals 10, or Z equals 10 as the Americans would say. And that means the wavelength is multiplied roughly by a factor of 10, right? So optical waves are like half a micron, that's the ones we use to see one another. Okay? So if you multiply that by 10, we're talking about something like 5 microns. In other words, what the near-infrared camera or MIRI can image. So it's perfect for trying to find very, very distant galaxies, which also means galaxies way back in time. Okay, so I'll tell you the current status and then tell you some of the new results that we have. So the first thing is what we call a point spread function, which means how, if you like, how precise the images are from this telescope. It's actually performing better than was expected, right? Which is great. It is really, really working well. The images are extremely sharp. But what's even more amazing, certainly to me, even, and I've been involved with the project for 20 years, is that those, as you saw with the James Webb mirror, there were individual 16 different hexagonal mirrors, and they were precisely aligned, and they stayed precisely aligned to a tiny fraction of the wavelength of optical light for days. Right? They're really, really precise. So the image, if you like, is extremely stable. Okay. Its sensitivity is actually better than expected. One thing that was a little bit, a difficulty, but at least now it stabilizes. The very lowest wavelengths of MIRI, the detector seems to be disimproving a bit at the time. Something in the order of 15% or thereabouts, but it is now stabilized, which it is probably something to do with the cosmic ray hits that the detector had. Another thing which is interesting for a couple of reasons, and was expected. The Webb telescope is hit by micrometeorites. There are plenty of micrometeorites out there, and they will hit the mirror, they will hit the structure of the telescope. The main structure where the instruments are contained, it's not an issue. I mean, they're basically well protected. But the mirror could be hit, and it's a beryllium, it's gold on the top and beryllium underneath, which is a very light element. And so when it's hit by a micrometeorite, it does hit. And there's been something like, I think it was about 50 hits since March 22, since it's been monitored. And with the exception of one hit, right, they're fine, it's nothing, absolutely nothing. The one hit could have been just a once-off event. Statistically, that's what it looks like. It was just a little bit unfortunate. It's not seriously affecting anything to do with the telescope. On the other hand, just as a precaution at the moment, basically what NASA are doing is not pointing it in the rain, so to speak. In other words, you get these showers of micrometeorites, particularly associated with various comets, and those are avoided. So you turn it away from the rain. Now, that may change over the next few years once we get a better idea of the statistics. But a wonderful development, which is really thanks to Europe and Arianespace, which was responsible for the Ariane rocket, was that nominally JWST was supposed to last 10 years. Because you're obviously pointing it this way and that way and so forth, and that uses up the fuel. But Arianespace was so precise at getting it to the right place in space that almost no extra fuel was used up. So there's enough propellant for 25 years on board. So, basically Arianespace were responsible for extending the mission, potentially the mission lifetime for another 15 years. Then, of course, the issue is, will it survive all the micrometeorites over 25 years? But, okay, it's a good problem to have. So, what new discoveries have we made? Well, I'll start from, our own solar system. And then kind of move outwards. And this is going to be a whirlwind tour in 30 minutes, okay? And I'm not doing justice to many of the new results that have come out. But I thought I'd show you some representative samples of some of the discoveries. Now, this object, of course, we're all very, I'm sure, we're familiar with, is Jupiter, taken with the JWST, and of course you have the famous great red spot, and you're seeing a lot of detail, a bit like the sort of detail you would see with the Hubble Space Telescope. But what's very interesting here is in the infrared, because this is an infrared image, you can see the aurora, right, which are on the north and the south poles of Jupiter, so that kind of reddish light either side. The Bally-Gally effect, right? Bally-Gally effect, I should say. So, this reminds me of one of the theatres in Trinity which had no light switches. So it was dependent upon the motion of the students or the lecturer. So, if you didn't move around enough, the lights would just go out. And then we'd have to sort of jump around, so motion sensors. That's an improvement you can do in here, right? So that's what Jupiter looks like, but I think this particular picture now of Uranus, where you can see the rings there around it, are absolutely fantastic. Because Uranus is pointing, we're looking at a pole, so these are kind of equatorial rings that you can see. You can see about 9 or so in there, and there's a total of 11 have been detected. But you can see the pole here, and also an extensive area around the pole, which actually people don't understand why this icy giant has this pole to one side at the moment, but it's something that's being worked on. And here you can see the various moons of, I think about 9 moons there. Uranus is about 27 or something of that order. So, I mean, they're beautiful images. It can tell you a lot about the rings in detail because basically the rings are like dust particles essentially, and so they radiate a lot in the infrared, and so that's why you can easily see them. But I mean, okay, to some degree, that's very, very interesting. But what I find particularly interesting is something like this, which is a spectrum of a comet. Now, the comet detected by JWST is the white one here. This blue one, in both cases, the blue comet is actually the Deep Impact mission, and this is a spectrum of comet Hartley. But you can see water in both cases, but carbon dioxide in the case of Hartley, and no carbon dioxide in the case of this short period comet Reed. And why is that important? It's because it starts to tell you about the constituents of the comets themselves. The short period comets versus the long period comets. Which ones have carbon dioxide on them, which is of course ice or frozen ice. But you can also see water ice on them as well. And this is very important we're trying to understand where exactly did these comets come from in terms of when the solar system formed. And so it looks like these short period comets probably came from the inner regions of the solar system, whereas of course we know the long period comets that come from much, much further out. So they have very different constituents. Now, moving away from our own solar system, this is an actual image of a planet, right? So this object here, hit the Parcus mission 65426b, is an actual planet around another star, and there is the image taken with NIRCam. That's where the star is, incidentally. This is the planet. Okay? We're not talking. The star is actually covered up in this case because it's so bright. There's a coronagraph that blocks the light. Here with MIRI, you can see the planet, and it is very, very clear. This is at 15 microns. Right? And the reason why that happens is that take the Earth. The Earth is at 300 degrees Kelvin, around 0 Celsius. That's what we figure. It actually radiates a lot of 10 micron light. That's why we can't do this from the Earth, because a lot of energy comes from the Earth at 10 microns. But that means when you look at a distant planet, you can actually go and pick the planet out much more easily, because the star wouldn't have so much 10 micron light because it's much hotter. However, the planet then will peak in terms of its light at 10 microns, just because of its heat. So we're detecting the planet that way and actually managing to image them. Some of you may have heard of a system called the TRAPPIST system. And the TRAPPIST system here, essentially, the bottom line from this is that the TRAPPIST system, TRAPPIST 1b, was imaged with JWST. It's seen in transit going across the star, but we can also image it when it's on either side of the star. We can actually measure the amount of light, I should say. And that tells us its temperature, and the temperature that was found for this object, because we know exactly how big it is. The temperature that was found is consistent with just being a rocky planet. Now this is interesting because TRAPPIST 1b is similar in mass to the Earth. Okay? So, using Webb, you've been able to tell, right, at least this Earth mass like planet is devoid, it's a bit like Mercury, it's purely rock. Now, that's not the case in many other planets, but it's interesting that we can actually measure that now. And we can look at, of course, hot Jupiters, for example, and this is a spectrum of a hot Jupiter. Now, the spectrum, we're breaking up the light, we're looking for certain elements, but in particular we're looking for certain molecules. Because when you go into the infrared, you can really look at different molecules. And that means, like in the case of the Earth, where there's oxygen molecules, nitrogen and so forth, and carbon dioxide, we can look for those. And what you see here is the different contributions from different molecules, including hydrogen sulfide, which is kind of like rotten eggs, that sort of smell. You have carbon dioxide, you have sulfur dioxide, and so forth, and methane and water, and all of those are in that spectrum. Okay? So we know exactly where those molecules will be, and there's a unique combination of those which will actually produce that spectrum. So let's start with stellar bursts. So this is a picture using the near-infrared camera, but also the mid-infrared camera as well. And so the reddish lines here is the mid-infrared camera, and the bluish are the shorter wavelengths. All right? But these are actually clouds in which new stars are forming. You can see the effects of the new stars at the top there. And those are regions of star formation. Stars in the Milky Way, roughly one new star forms per year. So it's a kind of easy figure to remember. The process, however, takes a couple of million years. Right? But the rate is about one new star a year. So why bother studying these objects? Well, if we work out how stars form now and they're forming all the time, then we can understand better the formation of our own solar system and systems around other stars. And this is typical kind of thing that we see, and this is called LINS 1527. But the star, the young star, is right in the middle here. It's just in this region, and it's actually obscured even to James Webb. But you can see these lobes of gas and dust which surround the new star. So it's a bit like what we call an hourglass, like, the egg timer. And this pattern is seen again and again when a new star forms. So our sun would have looked like that in its very, very early days, when it was, say, a couple 100,000 years old. And this is an image that was actually presented at the European Astronomical Society meeting in Poland this year to mark 1 year, basically, since operations of JWST. And what you, let me darken this now. So this is called Rho Ophiuchi. This is a new star forming region. It's one of the nearest ones to us. It's a couple of 100 light years away, 300, 400 light years roughly. Anyway, I just magnified a few bits of this image, because when you see an image like that, you think, wow, and all the rest. But the detail that's in there can be lost. So when you blow these up, these regions here are actually new star formation regions. So there's a young star here, and it's producing these jets of material, and likewise down here. These are stars rather like the sun when it was just a few 100,000 years old. And what I just want to do now, and hopefully this is going to behave itself, I'll show you a particular region in the sky which is forming new stars, and this is going to try and give you an idea of the level of detail we're talking about in JWST. So this is some of my homework. This is called IC348. It's actually star-forming region, and the stars are forming in these dark clouds. So if you go and look up at the Milky Way at night, you'll see plenty of stars. That's what the Milky Way is, but you'll also see dark lanes as well. And those dark lanes are not regions where there are no stars. They are regions where there's gas and dust, where new stars are forming, and that prevents us from seeing. But when you switch the infrared, you start to penetrate through this gas and dust. Okay? So we're actually just going to, this is about the area of the moon on the sky. We're just going to look at this little area here, okay? Just to show you the detail, level of detail. Now, this is an image taken with the VLT, the Very Large Telescope, ESO 8-meter telescope, okay? And it was taken a number of years back, but again, you can see these jets I was talking about. So there's a young star right in the middle here. It's actually, as we've discovered in the past couple of months with the James Webb, it is only a few thousand years old. This is a real baby when you're talking about young stars. And it's producing these jets, supersonic jets of material coming out from the star itself. And we can magnify that a bit more. That's what it looks like, okay? And this is a picture actually taken at 2.12 microns, so 4 times the wavelength of light in the infrared. Those are the supersonic jets. They're moving roughly 100 kilometers per second, right? One going this way, the other going this way, and produces shocks rather like Concorde used to produce in the as it travels supersonically through the air. Okay, so that's the that is the best image from the ground of the system. Okay, and I'm going to show you now, which was a press release last week from Baltimore, and this is Arlington State. So, bit of a difference, would you agree? And the young star is still obscure because it's covered with so much gas and dust. It's located right in the middle here. But you can see the jets coming out both sides, and the beautiful detail and the bow shots, as we call them as well. Okay? So that's why we go to space. The detail in that is absolutely amazing, I think. We can also look at objects that are called debris disks. So what actually happens is that when a new star forms, it has a disk around it which eventually forms planets. But just as in the case of our solar system, and the moon, when you see the moon, is cratered largely from a very early phase in the solar system. What happens is a lot of the bodies that form start colliding with one another, produce a lot of dust and debris, and that dust and debris forms. So the system could be something like 300 million years old or whatever, but it forms a disk around the star. So the star itself is again blocked, but you see these rings of material around there. But with JWST, and this is again with imaging with MIRI, you can actually see clumps of gas, clumps of dust gathering within these rings. Okay? Now it's important from the point of view of understanding the dynamics of these rings and what's going on. To see features like this, see how long they last. We expect them to disappear in a few years in some cases and so forth. But these are, if you like, remnants from what we call planetesimals hitting one another and ending up producing loads of dust. And this is also a picture of an object that some of you will know, a supernova. Now, a supernova is when you have a massive star at the end of its life. A massive star don't live terribly long, maybe 10. You get blasé about the figures, 10 million, 30 million years. It's not very long when you compare it to the sun, which is 1,000 million years old. But they do explode and they produce what we call a supernova remnant. Now, this is one which is in the constellation Cassiopeia. And this circular thing here, which has been seen in X-rays and in radio waves. There's nothing too strange about that. It's an explosion from the supernova, and it's moving outwards with time, away from the center, which is here. And you sometimes see the center what we call a neutron star, a pulsar. Fine, but what's different about this is Mary, it is showing you where the dust is, right? There's actually dust. You can see the dust in detail in here. We can look at the composition of what that dust is made of. In other words, whether it's very small particles, very large particles, what's actually there. And why is that important? It's important because it's this dust which gives rise to you and me. Okay? Because it's the dust from supernova explosions, or maybe from what are called asymptotic giant branch stars, that give the sun, when it was formed 5,000 million years ago, it gives us the elements from which we formed, from which. So it's important to understand what type of dust is there, how much dust is produced by typical supernova, and so forth. So the only way of exploring that is to work in the infrared. Now, another example of a kind of, if you like, stellar death is this Wolf-Rayet star. Again, a Wolf-Rayet star is the end of the life of a very luminous star. And when this was seen first, people started to think, God, something's going on in the telescope, right? All these rings. But it turns out this is a Wolf-Rayet system, which actually is a binary. The binary goes around in about 8 years, but the binary is in a, if you like, a perfect circular orbit. One star gets closer to the other, and when that happens, it disturbs the star and produces rings of dust. So these are actually moving outwards from the Wolf-Rayet star and correspond to events roughly every 8 years. Okay? But again, it's another way in which dust is being sent into the interstellar medium. And again, dust that you and I will be made up of. So we really want to know where is most of this dust coming from. Okay, now let's move really far out now and look at galaxies. So this particular galaxy, well, let me say the background first. What happens with a galaxy, a cluster of galaxies, is that the cluster can actually focus the light of distant objects behind it, right? So it's a lens. Now, it's not just the galaxies that you see. Probably many of you have heard of dark matter. There's a lot of dark matter, much more dark matter than there is ordinary matter in these clusters of galaxies. And that dark matter bends light, right? And it bends light, as explained many, many years ago by Albert Einstein. It actually bends light, and therefore it can focus light, because a lens does exactly that, it bends light. Okay? Now, why is that important? Well, it means that effectively you've got a telescope in space, right? In addition to the telescope you have in our backyard on 1.5 million kilometers. Why? Because it's actually focusing very, very distant galaxies, ones that you wouldn't normally see, because they're way too faint. And you can see a lot of detail in them. Now, this system, this particular cluster is known as El Gordo, which just means the fat one. Okay? And these images, by the way, are from a lady, Brenda Fry, who actually worked in Dublin for many years and then moved to the University of Arizona. So she's involved in many of the JWST missions to do with observations of distant galaxies. So let me document this again. Okay. So this is the cluster itself. This is the cluster of galaxies, right? Well, what you see here, this is called La Flaca, which means the skinny one. Okay. So great names for this. I wasn't responsible. I think it was Brenda. That's actually an image of a galaxy, one galaxy, which is much, much further away from the cluster. Now, the cluster, I think, is at about a redshift about 1.5, 1 or so. But these are typically at redshifts of 10 or 20 or 15 or thereabouts. Okay. So there's, if you blow this up, and again, as I mentioned, you have to really, you can look at this image and it looks very impressive, but there's a hell of a lot of detail. So if you blow this area up, there's El Flaca, and you can see actually these are bits of the galaxy in gravitational lens. So this is one galaxy, which is then all spread out. I want to show you a particularly amazing an example in a few moments. And this is known as El Anzuelo. Anzuelo means a fish hook. Okay? So this is a fish hook. And again, that's over here. This is one galaxy that's just being imaged by the mass of material that's okay? So that's a gravitational lens. Here's, to me, it's an absolutely amazing image. Why? Because this is known, again, we're talking about another cluster. The number is not important. But this sort of arc here is known as the sunrise arc. Okay? And again, it's an image of a galaxy. The galaxy is actually on a redshift of 6.2. But this is actually one star. So if you get it in this lens in just the right point, this is actually what astronomers call a B-type star. It's actually a binary web. And Arundel, I think, was Old English for the ancient one. Okay. But that is an individual star at a redshift of 6.2. Okay. So we're actually imaging stars. In one star at 6.2, you can obviously use this phenomena of the gravitational lens to enhance our view of very, very distant systems. And the important take-home message from this is that we're actually able to do this because we're operating in infrared, because those high redshift galaxies and the light is optical, right, when it leaves, but when it's a redshift of 6.2, the light is already stretched into the infrared. And so to see all of this, we need to move to the infrared. When we work in the infrared, we also are able to push the boundaries of what our gravitational lenses can do even further. So we can use the lensing phenomena to understand what's happening. So the last two or so slides, I just want to show you what even more distant systems are like, and we're seeing loads of them now. This is a galaxy, right? And it's on a redshift of 10.6, maybe 11. So it is, we're talking 400 or roughly million years after the Big Bang. It's already formed a galaxy. But what's even more surprising, right? So this is the spectrum of that galaxy, which is at only 430 million years after the Big Bang. And we can identify a lot of the elements that are already present in the galaxy, which I find absolutely astounding that at that distance already it is formed a lot of the elements that we're familiar with now. So what we are seeing when we look at these distant systems, and here's a kind of just a gallery of some of them, right? So these are all redshift 9, 10, 11, 12, we're going up to 13, right? So we're talking back to 300 million years or so after the Big Bang. When we count the number of them, the bottom line is this, that it looks like there's actually lots of them. We kind of expect it to be less and less as you go closer and closer to the Big Bang. But it looks now like galaxies form very, very early on. And so, from the point of view of the theoreticians, and there were some of the theoreticians there last week in Baltimore, this is very upsetting. Right? Because it is really, really pushing their models to try and explain all the numbers of these high redshift galaxies that we're finding. And some of these galaxies, by the way, and I'm talking 400 million years after the Big Bang, already look like spiral systems as far as we can tell. Okay. So, yeah, they're going to pin them to their colours, so to speak, to try and explain it. Okay, so to summarise, JWST was very successfully launched. It was amazing, to be honest, in retrospect. All of these steps worked out perfectly. We've got some really wonderful results from it. As a result of our involvement and the UK involvement in European Space Agency,